Welcome back, everybody. The topic of this presentation is a second type of cache designs or cache organization, and that is the so-called set associative cache designs. And recall the four questions in the context of a memory hierarchy that, if answered, one would tell everything about that cache design. So we'll discuss and talk about this set associative cache designs within the context of answering those four questions, as well as we did for the case of the so-called direct mapped cache organization or design that we talked in the previous video. So the idea of the n-way set associative cache designs is to take all the entries into the cache and split them, partition them into a number of sets, where each set contains a number n of entries or blocks. Then the block number will determine which set that block maps to into the cache. And we'll see later on that in answering the question of how to find where the data is in the cache, and if it is there or not, we'll search all the entries in a given set at the same time, and that will require some additional hardware as penalty, but will have some other benefits compared to the direct mapped cache designs. So the first question, where can a block be placed in the cache? If in the direct mapped cache design or cache organization that we talked in the previous video, set a memory address, like in this example, address 12, mapped to only one unique entry or block into the cache. And this case, and the case of a two-way set associative cache design, so in this case, n is equal to 2, meaning that the cache, which has 8 entries, is split into a number of sets where each set contains 2 blocks. So the 2 blocks 0 and 1 form the first set, and then the second set is formed by the next 2 cache blocks or entries, and so on. So we have 4 sets. In this case, the address 12 from the main memory maps to this set, set 0 or index 0, found out through a similar operation, modulo operation, given by 12 modulo 4, where 4 is the number of sets. Remember, we have 4 sets, and each set contains 2 cache entries or 2 cache blocks. So that is 0, and that data will be fetched and placed into any of these 2 blocks or entries into the into this set index 0. And as you can imagine, the fact that we now map one memory address to 2 different blocks that form this set will have the ability to not overwrite right away some data that might have been written into that cache block, as in the direct map cache organization, where overwriting would have been detrimental to the first block that was written into that block entry. And in this case, we have 2 possibilities, 2 different blocks where that data can be written into that set, and the way we'll be placing into this block or that block will be based on which of the 2 blocks might have been the least recently utilized one. And the least recently utilized one would be the one that would be overwritten, and this way still keep into the cache, not overwrite over it, the data, the block that was most recently utilized, and in that way exploit and benefit that temporal locality that we're talking in the previous video, that blocks that have been more recently utilized will be kept or will be preserved in the cache, and this way increase the chances for more hits into that cache design, and not required to pay the penalty of going to the main memory and fetch data that in the case of the direct mapped cache design might have been overwritten too quickly. So that is the idea of organizing this cache in a two-way set associative cache design. Now, the question number 2 was about how a block can be found if it is in the cache or not. Things complicated, but not that much. This diagram is very similar to the one that we saw in the previous video when we talked about direct mapped cache designs. The difference here is that now the cache is organized, is split into sets, or in this case, a set is formed by 4 blocks. 1, 2, 3, 4. So if the cache, the initial cache capacity is again 1024 different entries. Now those entries are organized in sets of 4 blocks each, and because of that we have only 256 different sets that to be able to index in order to find out which set a certain main memory address might be mapped to, would only need 8 bits and not 10 like we had in the previous example to be able to find out the index of that set. So in this case, splitting the address that the processor is asking about is done by as shown over here. We take only the least significant 8 bits out of that memory to find out and identify the set in which the data that the processor is asking about from that address might be located in. Now the challenge here, or the complexity, is that that data can be in any of the 4 blocks that form that set. So, and to find that out, we'll have to replicate that trick of having this comparator that checks the content of the tag field in that cache entry to verify, to check whether that is the same as the tag of the address that the processor is asking about. And if any of these 4 comparators gives us logic 1, and then additionally the valid bit is true, is 1, then one of the 4 logic gates will give us a logic 1 that will give us through this OR gate a logic 1 that will signify that we have a hit. The data that the processor is asking about from the main memory address of 32 bits as specified here, the data from that address is indeed cached, exists in one of the 4 blocks of this set. It is there because the tag is the same, it is valid, and then if that is the case, then we have a hit, and that data can be retrieved through now a circuit that involves a multiplexer that will multiplex any of the 4 different blocks to the output through this multiplexer that will be controlled accordingly and conveniently by the output of the 4 AND logic gates. Now, as you can see, the hardware to find out whether there is a hit and then to retrieve the data out of the cache is a little bit more complex when we organize the cache in this 4-way set associative cache organization. However, this cache design will benefit better from the fact that the data doesn't map anymore only to one unique location inside the cache, and it can be written in 4 different locations, and in this way exploiting better the temporal locality. We will not have to overwrite the same cache entry as many times as we might in the case of a direct mapped cache design. And all in all, this cache design will improve the number of times that the processor will hit, and the cache will have hits rather than misses. The penalty is that we have to spend more logic circuitry, so the area will increase, and the time for the data from any of those 4 blocks forming this set in this example will have to also go through this multiplexer that adds delay for the data to get out of the cache and be passed to the processor. So the delay will be a little bit worse in this case, but overall this cache design is more practical and better than the previous direct mapped cache design. Now, the third question was about which block should be replaced on a miss. So if the processor is asking about the data from the main memory at an address that is specified here on 32 bits, the cache controller, the cache looks inside itself and finds out that the data from that address is not in any of the 4 blocks that form this set. So that is the case of a miss. In that case, the block corresponding to that main memory address will have to be fetched from the main memory and be placed in one of the 4 blocks. The question here is in which of the 4 blocks that form this set the data will be placed. What policy should one use in overwriting these 4 blocks, 4 entries that form this set with the newly fetched data? And one of the most popular and practical in terms of how easy it is to implement approach is to use a writing policy called the least recently utilized, which is to say that the entry of the 4 blocks that was the least recently utilized will be the one that will be overwritten. And that is the answer to that question in the case of the set associative or fully associative cache organization or cache designs. The fourth question, what happens on a write, depends again, like in the case of the direct mapped cache design, whether we are implementing a write through or a write back cache design. So I won't spend time on this because it's the same as in the previous cache design. I only wanted to say one more thing, and that is the fact that the special case, the extreme case, when the whole cache is treated as a set, meaning that the cache now is partitioned into just one single big set, where n is the number of entries that we have in the cache. So it's not like what we had here when this 8 entries cache is split into 4 sets, where each set contained 2 blocks or 2 lines. Now the cache is one big set of its own with 8 different blocks or entries into that set. And because of that, the address from the main memory maps to just that one single set, and the data can be placed in any of the entries, any of the blocks that from that set. This is an extreme case of this n-way set associative cache organization design, where instead of having a certain number of sets, we have just one big set, and that set would be operated similarly to how you would have operated an individual set in this case, a 2-way set associative cache design. Now this is at one end of the spectrum. The direct map is at the other end of the spectrum, where the data can be mapped to only one unique location. Here, the data can be mapped to any of the entries into the cache. The n-way set associative cache design is a middle ground, a compromise between the 2 extremes, and most practical implementations would employ and implement this cache design. The n-way set associative cache organization, which we'll talk more about in the follow-up course of this course that I will teach in the fall, computer architecture, for those who will be interested to take that course. That's it. I'll see you in the next